Okay, hi everyone. My name is Pakshi, and today I'll be talking about robust linear regression, and more specifically, how to get optimal rates for this problem in polynomial time. This is joint work with Adarsh Prashad, who was a PhD student at CMU until very recently. Okay, so let me begin with some background on robust linear regression and set up the problem that we will be focusing on in this talk. Okay, so in the canonical linear regression problem, we are given as input n samples, where each sample is a tuple of the form x1, y1, where we refer to the x is as the covariates and the y's as the response. And each of these is sampled from some distribution d. We also assume that the covariance of the distribution, when restricted to the covariates, that is the x's, is an arbitrary unknown d by d PSD matrix sigma. And we also assume that the mean is 0. This we can reduce to this case without loss of generality, so let's not worry too much about that. And we also, it would be also good to keep in mind a simple linear model where the way the response or the y's are generated is as follows. So there is some underlying hyperplane theta star, which is the optimal hyperplane, and the xi's are drawn from some distribution with covariance sigma. And the y's are generated by taking the inner product of the xi's with this optimal hyperplane theta star and adding some independent mean zero noise, such as the standard Gaussian. This is a simplification of the models that we consider in this talk, but it'll be good to keep in mind this concrete example. Okay, so given this, the picture might now look like the following. Here we're given the data points in white. So here the x's are one-dimensional. And the goal is to simply find a hyperplane theta, which is close to the optimal hyperplane theta star. And in this picture, the optimal hyperplane theta star is just the best fit curve here given in orange. Okay, so that's a brief recap of the canonical linear regression problem. And this problem is one of the most fundamental and well-studied problems in statistics and machine learning, as you all know. And it admits a very simple algorithm. So essentially, any algorithm that minimizes the least squares objective suffices to solve this problem. Let me quickly recall what the least squares objective is. It is simply the average over the sum of squares of the error incurred by each of the training points or the pairs xi, yi with respect to a candidate hyperplane theta. And in this talk, we'll use this notation error of theta to denote the least squares cost and to make sure that everyone is on the same page. If there is truly a hyperplane that fits all of the points, then this error of theta will be 0, minimized over all such hyperplanes. Okay. So in this work, we are in fact interested in this robust variant of this problem, where the robust variant is defined as follows. So we are still given n samples of the form x, xi, yi from the distribution. But now an adversary is allowed to come in and change an epsilon fraction of the xi and yi's, and the adversary is allowed to change this in an arbitrary way. So the adversary can either add or remove points or move the points around, and then we make no assumption on what the adversary does. Also, the adversary is allowed to corrupt both the x's and the y's, and this model is known as the strong contamination model and generalizes several well-studied problems, including the Huber and TV distance corruption models. Okay, so the picture now looks something like this. As before, we have these true data points sampled from a distribution in white, and then the adversary comes along and adds these points in red. And our goal is to still output a hyperplane that is close to the optimal hyperplane for the uncorrupted points. So a bit more formally, we output a candidate hyperplane theta, which is close to the true hyperplane theta star in this scaled L2 norm, where the scaling is determined by the covariance of the x's. I will get into why this is the right notion of recovering the hyperplane a bit later in the talk, but for now, let's go with this objective to define the problem concretely. And what we want from this is that we want it to be upper bounded by some function of epsilon, the smallest possible function of epsilon, times the least squares objective of the optimal hyperplane. So essentially, we want to get close to obtaining the error that is achieved by the optimal hyperplane. Okay, cool. So given the setup, let me mention some key points that we would want from our modeling assumptions. So we would like to make the minimal possible assumptions on the distribution over the axis. We would also like to capture a large class of linear models, including ones where the noise is independent or correlated or arbitrary and so on. And we would want to get the best function of epsilon here to make sure that we converge to the true hyperplane as quickly as possible. And in particular, we would require, at the very least, that this function of epsilon goes to 0 as epsilon goes to 0. So in other words, in the limit when there are no outliers, we should be able to recover the optimal hyperplane. Okay, so with that setup in mind, I'll now describe the results that we obtained in this work. So let's start with the weakest possible assumption on the covariance of the axis. So the distribution, so the weakest possible assumption here would be to simply assume that the distribution has bounded covariance. And in fact, we show that this assumption is in fact too weak. And in the robust setting, so for robust linear regression under bounded covariance, there is no estimator that can recover a vector that is close to the true hyperplane in this setting. So in particular, there is no estimator which recovers a vector theta such that this function goes to 0 as epsilon goes to 0. Okay, so a few comments are now in order. So this result is information theoretic. It's not a computational hardness result. It says even if we're given infinite samples, it is impossible to recover a hyperplane that converges to the true hyperplane as the fraction of outliers tends to 0. Okay, so the hard instance you construct is based on the student's t distribution, and this hard instance is non-standard compared to other lower bounds that are proved in either this work or closely related works. So check it out. And the distribution that we pick, so the student t distribution does not have 2 plus delta moments for any delta greater than 0. These are infinite. And also to show this hardness, our regression model assumes that there is no noise. So this is really quite a strong lower bound. Okay, but that's not the end of the story. So one natural strengthening of the bounded covariance assumption is to consider distributions which are hyperconductive. So in one line, these are the distributions for which the low degree moments are well concentrated. And now I'll define what hyperconductivity means a bit more formally. So distribution D is C comma K hyperconductive if for all vectors V, the following inequality holds. And it's a lot to parse, so let's parse it carefully. So the left-hand side here has a projection of the random variable x drawn from the distribution D along some direction V. We send out this random variable to have mean 0. This is subtracting its expectation of along this direction. And then we look at the 2kth power of this quantity. So if we take the expectation over all such x's, the left-hand side gives us the centralized 2kth moment along direction v. Hypercontractivity asserts that this is bounded by some constant times the variance along direction v raised to the kth power. Okay, so this is a well-studied analytic condition, and it shows up in the context of robust estimators for mean, covariance, mixtures of Gaussians, subspace recovery, and so on. And it captures a large family of heavy-tailed distributions. In particular, it captures the following well-studied important families of distributions, including Gaussians, uniform distributions of the hypercuban sphere, strongly log concave distributions, Polar distributions, and so on. And in the context of robust regression, Clivens, Kothari, and Mecca introduced a strengthening of this property, which they refer to as certifiable hypercontractivity. And this is what we will work with. And I will ignore the distinction between hypercontractivity and certifiable hypercontractivity for now. But let me say that all of the examples that I mentioned here for the distributions that are hyperconductive are also certifiably hyperconductive. Okay, so with that in mind, I'll describe what our main result is. It says the following. So if the distribution over the x's, which I denote by d sub x, is c comma k hypercontractive, there exists an estimator theta with the following properties. The number of samples required to compute this estimator is d over epsilon to the omega k. The running time required to compute this estimator is n to the of k. And the error guarantee that we get is that the function of epsilon is epsilon to the 1 minus 1 over k times the least squares error. And this is an upper bound on how close theta is to theta star, where theta star is the optimal hyperplane in this scaled L to norm. Okay, so that is the main result. And let me provide some context for it. So the dependence here on epsilon is actually optimal, and we prove a matching lower bound. As I alluded to earlier, this notion of parameter recovery in the scale L2 norm implies a generalization bound. So the estimator that we recovered, which is theta star, the error, the least squares error of this, is upper bounded by 1 plus epsilon to the 2 minus 2 or k times the optimal least squares error for the optimal hyperplane. And note that the transformation from this kind of guaranteed, this one is simply squaring this function of epsilon. Okay. So our estimator is based on the sum of squares hierarchy. And not only do we provide one single estimator for the independent noise case, we show that we have a general framework which extends to other linear models where the noise may not be independent, and it may be correlated or arbitrary, and so on. And I'll describe this framework later in the talk. Okay, so to contextualize our result a bit more, let me mention some of the prior work on this problem. The most closely related work to this one is by Gleivans, Kothari, and Mecca, who get an epsilon to the half minus 1 over k dependence, as opposed to 1 minus 1 over k that we get. And this holds for all k. Their assumption is the same. They also assume C, k hyperconductivity. There's another paper by Prasad, Sugala, Balakrishnan, and Ravi Kumar, which gets an epsilon times kappa squared dependence, where kappa squared is the condition number of the covariance matrix sigma. However, in general, the condition number can be quite large and even dimension dependent. So this guarantee is not that desirable in such a setting, and it holds only for k equals 4. Okay, and since this is such an active area of research, there has been some concurrent work since we first posted this paper. And in a paper by Zhu, Jiao, and Steinhardt, they obtained an epsilon to 1 minus 2 over k dependence, which improves this Gleivans, Kothari, Mecca dependence, but it's still not quite optimal. And there's also a paper by Charab Namjari et al., which gets the same dependence. Okay. So I would like to point out that prior and concurrent work are not able to get this epsilon to the 1 minus 1 over k dependence when the noise is independent of the covariance. And this is the setting that I will focus on for the remainder of the talk. Okay, so recall the linear model that we were working with is that there is some optimal hyperplane theta star. The xi's are drawn from some hyperconductive distribution, and the y's, the corresponding the corresponding y's are generated by taking the inner product of xi with theta star and adding some independent random noise sigma. Our main conceptual contribution here is that we need to algorithmically exploit the independence of the noise and the covariates in order to obtain optimal rates as a function of epsilon. In fact, we introduce an analytic property of distributions over regression instances that generalizes the independent noise model, and we call this property negatively correlated moments. So in a line, this intuitively means that the low degree moments of the noise and the covariates, which are the xi's, are negatively correlated. Okay, so let me define this a bit more formally. So for a distribution D over RD cross R, which is what a regression instance looks like, has k negatively correlated moments if for all v the following inequality holds. Okay, so here on the left-hand side, we have the projection of the covariates x along some direction v, and we raise this quantity to the kth power. And then we multiply this quantity by y minus x times theta star. Now recall y minus x times theta star is the noise that was added in the regression instance. And we look at the kth power of this. Now taking the expectation over the x comma y drawn from this distribution, what we get on the left-hand side here is the kth moment of the joint random variable. And the negatively correlated moments condition says that this is upper bounded by the kth moment of the individual parts. So the kth moment of the covariates times the kth moment of the noise. And it is easy to see that if the noise were independent of the covariates, then this inequality trivially holds. Okay, so our main theorem, which obtains this rate epsilon to the 1 minus 1 over k, generalizes to all regression instances that satisfy this property. Next, I'll show how we actually use this analytic condition for distributions to design estimators. Okay, so let's get into designing this robust estimator. And for the time being, let's ignore computational aspects involved in designing these estimators, and assume that we have access to unbounded computation. Okay, so in this setting, a naive estimator that one might come up with is the following. So let W be a vector length n, which represents n indicator variables, out of which only 1 minus epsilon fraction are 1 and the rest are 0. So intuitively, this vector W picks a subset of size 1 minus epsilon. For any such subset, we can look at the least squares objective on the corresponding subset. And the way we design the estimator could simply be to search over all subsets of size 1 minus epsilon and pick the one that minimizes the least squares objective, and look at the estimator that is given by the least squares objective on this subset. Okay, so this is a brute force algorithm, and since it searches over all the subsets of size 1 minus epsilon and picks the one that minimizes the objective. Okay, so this is a valid, robust estimator, and even though it takes exponential time, it is not clear whether this estimator suffices to get the optimal rate. In fact, we get stuck at 1 minus epsilon to the 1 minus 2 k, but there is no inherent reason why this should not work on its own. In other words, it's unclear whether it suffices. Okay, so let me now describe the estimator that we can prove works. Again, we minimize the least squares objective over a subset of 1 minus epsilon fraction of points, such that the following additional constraints also hold. So in particular, we want that the uniform distribution over the set of points, the xi's that were picked by our indicator, the wi, is hyperconductive. We know that the true samples satisfy this property, so it is valid to enforce this as an additional constraint. Okay. We also want that the gradient of the loss evaluated for the candidate hyperplane on the subset of points that we pick is 0. So this is a non-standard constraint, since typically the minimizer of a convex objective satisfies the property that it is locally optimum, and that the gradient of the objective function is 0. But we need to enforce this constraint explicitly. And finally, we need that the joint distribution over the xi's and the yi's picked by the algorithm, so picked by these indicators wi, has negatively correlated moments. And what we show is that this estimator, like the estimator that is obtained by solving this system of equations, in fact returns a theta star which achieves the optimal rate. Okay, so a priori, this system of constraints may seem arbitrary, but what we can show is that all of these constraints can be captured by a polynomial system. So that would be the first step. And even though solving polynomial systems is in general pretty hard, we will show that we can come up with good convex relaxations of this. Okay, so let me now briefly describe how to formulate each of these constraints as a polynomial system. Let's start with the indicator constraints. This is by now fairly standard in the robust statistics literature. And we can simply do this by setting each of the wi's to satisfy wi square equals wi. This forces the wi's to be either 0 or 1 and behave as indicators. To pick a subset of size 1 minus epsilon times n, we can simply set the sum of the wi's to be that, and this is a linear constraint. Okay, so next we can show how to enforce hyperconductivity, and this is also standard in the literature for robust statistics now for problems like mean and covariance estimation. But what we can do is simply look at the uniform distribution, which is the average over the set of points that we pick, which are indicated by the wi's, and enforce the definition of hyperconductivity, which on the left-hand side has the kth, 2kth moment, and we show this is upper bounded, and enforce that this is upper bounded by the variance of these samples raised to the power k. Okay, the gradient condition is again simply a linear function, which says, if you look at any direction v, then the gradient of the loss, which is given by this function here, which is the average of the error that we incur on each sample, is 0. Okay. And finally, we consider what is the most important constraint here, which is a proxy for independence of the noise and the covariates. And in some sense, this was our starting point. So if we want to solve the problem where the noise and the covariates are independent, and we want to formulate it as a polynomial constraint, a priori it is not clear how to do this. But instead, what we showed was that if we relax independence to this polynomial constraint of negatively correlated moments, of the low degree negatively correlated yet low degree moments, then this relaxation actually suffices to get the optimal rate. And just the definition of negatively correlated moments lends itself easily to be stated as a polynomial inequality. And I won't get into the details of this, but this is the expression. The high-level takeaway here is that we can think of this negatively correlated moments constraint as a polynomial relaxation of independence between two random variables, and I think this is a general idea that might find applications elsewhere. Okay, so next I'll briefly describe how to get efficiently computable estimators instead of this potentially exponential time solution to the polynomial system that I just described. And the main idea here is to use the sum of squares hierarchy of convex relaxations for polynomial systems. So our approach follows this long line of work on the proofs to algorithms paradigm using sum of squares relaxations. And it's a bit hard to get into the technical details of this, so I'll give a high-level overview. And what this means is that we consider essentially a hierarchy of convex relaxations, which are increasingly tighter for the polynomial system that I described on the previous slide. In order to argue correctness of this, convex relaxation, we show that there exists an easy proof of the following fact. So, given the constraints that the candidate hyperplane satisfies, the polynomial constraints I mentioned before, we show that the resulting hyperplane must be close to the true hyperplane in the scale L to norm. And an easy proof of this fact corresponds to an efficient algorithm, which is what the proofs to algorithms paradigm refers to. Okay, so we show that the proof of this fact is captured by a degree k sum of squares proof system, and which immediately implies using known machinery and n to the order k algorithm for this problem. So some challenges here that we show how to resolve in our paper include that the standard argument for showing such a proof does not really work, and we have a fairly involved proof which uses each of the constraints that we introduced multiple times. So unfortunately, there is no brief description of this proof, so I refer you to the technical overview section of our paper, which describes this proof in detail. And also, the negatively correlated moments condition, even though it is now a polynomial inequality, it is unclear whether there is a sum of squares proof of this. And instead of making additional assumptions on our distribution for this to have a sum of squares proof, we instead relax this condition even further and show that it can be implemented by the sum of squares proof system. Okay, so let me conclude with some open questions and directions for future work. Some concrete open questions include improving the sample complexity, which in our case was d over epsilon to the k, while maintaining the right dependence on epsilon and the rate, and being able to have the estimate be computable in polynomial time. Another open question is to obtain polynomial time estimators that achieve O tilde of epsilon rate for sub-Gaussian distributions. So currently, our estimators obtain quasi-polynomial time algorithms for such sub-Gaussian distributions. And for the special case of Gaussians, polynomial time estimator achieving O tilde epsilon rate is known. And this was in this paper by Dyke, Nicholas, Cohen, and Stewart. I also think it's interesting to consider finding estimators that achieve optimal rate for problems like sparse regression, logistical regression, and in general, the so-called generalized linear models. Okay, apart from regression and robust variance, I think it's also interesting to explore efficiently computable estimators which achieve optimal rates for robust and heavy-tailed statistics problems. So for instance, for heavy-tailed covariance regression, there are some really cool open problems, and there's recent work by Charab Namjari et al. And for robust proper learning of, say, mixtures of Gaussians, we can't really get optimal rates, but we can get, a polynomial factor worse in some recent work. And for a weaker problem where you're allowed to improper learning for a mixture of Gaussians, a recent result by Leon Wojtwa shows that you can in fact get this O tilde epsilon rate. Okay, so I'll stop here and thank you.